Hello, calculus. We're looking at this on the 16th, so 11/16, and that is going to be, we're going to be talking about a couple things, so I won't really title this lesson maybe till the end. So we have been looking at the first derivative test, and let me remind you what that looked like. It said if you had a point and you suspected that it might be a maximum point, a relative maximum point, or perhaps an absolute here, if it's not at an end point, then you can look at the derivative on either side, and we found that if the derivative to the left was positive and the derivative to the right is negative, then that would create a max point, or relative max point. Sometimes we call them local maximums. And the other way, if you're looking at a point and you're suspecting it might be a minimum point, you would check the derivative to the left, and if it really was a minimum point, the derivative to the left would be a negative, and the derivative to the right should be a positive. Then you would have a relative min. So we were getting to those problems, and let me take it just a baby step further to see how that would go. Let me straighten up the camera for a minute. While I'm doing that, would you take that graph, and I want you to take 1, 2, 3, 4, 5, 6, 7, and draw the slope at those 7 points. I straighten up the camera a little bit. See if this helps. I don't know, maybe it was okay. Alright, so we have a slope here that's fairly steep, less steep, a slope here, less steep, no slope there, slope here, and slope here. Let's put in some imaginary numbers in that. We're going to make them up, but they're going to be plausible. So this looks like a negative, very high sloping negative value. This is less of a slope at this point, -2, -1, less slope, and still in the negative direction. Negative slopes, positive slopes, 0, maybe 1, 2, and this looked like it jumped up to 4. I probably got that a little sharper of a slope tangent line than I should. So, but I want you to observe that the slopes, as we go from left to right, the derivatives, which are slopes, the derivatives are getting higher, from a -3 to a +4. So derivatives are increasing along that curve. So if a function, if the first derivative f prime is increasing on an interval, this is the type of shape it will always have, and we call that concave upward. It's a smiler. So the derivatives are increasing in that it creates a concave upward graph. So let's see how it works when it goes the other way. So here we have a function. Here's our 7 points. Draw the slopes, tangent lines at each point. And let's put in some numbers. This is a positive, say 3, and 2, 1, 0, -1, -2, -3. So what's happening the slopes from left to right this time? Note, from left to right, the slopes are getting lower. So derivatives are decreasing, and that is called concave downward. Alright, so before we leave this idea, I just want to establish that when we have a concave upward, we're going to look for slopes that are increasing across from left to right, and when it's concave downward, the slopes are going to be decreasing from left to right. So, what can I say? It would be sort of a pain to have to take a function and find where its derivative is 0, and then look at several points to the left, test points, and several points to the right, test points, and see if you have this pattern, or perhaps neither. So that would take a lot of test points. So there's a much quicker way to find the concavity of a graph. So I will reveal that way. And here's how it works. The test for concavity, and that when I say concavity, I want to know if it's concave up or concave down. That's the only thing I need to know. And the test for concavity actually uses the second derivatives, which is super cool. So if the second derivative is positive, that means that we have a graph that is concave upwards. And if we have a graph where the second derivative is negative, it is concave downward. So, no test points to speak of. So let's look at how we could figure that out. Suppose we had f of x equals x to the 4th minus 4x cubed. So go ahead and take the first derivative and then the second derivative. And the second derivative. And now that we have the second derivative, let's find where it is 0. So we're going to set this equal to 0. And factor it. Pull out a 12x and we get an x minus 2. So setting each of those factors equal to 0, we get x equals 0 and x equals 2. So that's going to create a little bit of a test situation, but nothing like what I was describing with all of these test points. So let's find those. So we go from negative infinity to 0 to 2 to positive infinity. Not drawn to scale. So let's go ahead and observe what's happening to the second derivative in these intervals. So I will do a test point here in this interval. I'm going to test -1, and I'm going to put it in the second derivative. So when I do that, I do get a positive answer. And now I'm going to test 1 in this interval. When I put it in the second derivative, I get a negative answer. Then I'm going to test 3 in this interval, and I'm going to get a positive answer. So you can check that out for yourself by plugging those in. And that means I have a smiler, concave up, then I have a concave downward, and then I have a concave upward. So we know a lot from the second derivative. That's going to lead us to something called the second derivative test, but that is for another day, or another night. So let's go ahead and call it a night, and we're going to catch up in our classwork before I go on from here. So, over and out.